Through this video, we will explore the mean value theorem, which is one of the most important theorems in real analysis. Mean value theorem connects the values of a function to values of its derivatives, and that is how it gains its importance. But before we do that, we have to first need a simpler version of the mean value theorem, which is called Rolle's theorem. So what do we have? We have a function f, which is a function from I to r, where I is equal to the interval ab, and f is continuous on ab, and f is differentiable for all x in open AB, and f of A is equal to 0 is equal to f of B. Then there exists a C in AB such that f dash of C is equal to 0. The basic idea of the proof is that this function has to attain an extremum at some point in open AB, and at that point f dash of C has to be 0. So that is the idea. Now let us turn this idea into a proof. If f is constant 0, then obviously f dash of C is 0 everywhere. So we can assume that f is not constant 0. So assume that f of x is greater than 0 for some x in AB. Thus, supremum of f of x such that x belongs to I is strictly greater than 0 and is attained at some point C in open AB. Why it has to be in open AB? Because at A and B we know that the function's value is equal to 0, but the supremum is greater than 0, so it cannot be at A or B. Because C belongs to AB, so C belongs to AB implies that f dash of C exists. But if f dash of C exists and the fact that C is a maximum implies that, so this plus C is maximum implies that f dash of C is equal to 0. Now this does not complete the proof because we have assumed here that f of x is greater than 0 for some x in AB. Now we have to see the case when f of x is less than or equal to 0 for every x in AB. So assume that f of x is less than or equal to 0 for every x in AB. So what do? You look at minus f. Now minus f is greater than or equal to 0 for every x in AB. From the earlier argument, we see that there exists some C in AB such that minus f dash at C is equal to 0. But this is equal to minus of f dash of C. So at that same point C, if wherever minus f dash of C is 0, f dash of C will also have to be 0. And thus we get a point C where f dash of C is equal to 0, even in this case. Let us now try to see what this theorem is telling geometrically. So geometrically what this is saying is we have a function f such that at A this is equal to 0 and B this is equal to 0. The function is 0 at A and B. And the function is not constant 0. So it has to increase, decrease, etc. So at some point it will have a maximum, and that at that maximum point it will have the derivative 0. So that's what it is saying. Finally, we are ready to state and prove mean value theorem. Okay. Suppose f is continuous on AB and f has derivative on open AB. Then there exists a C in open AB such that f of B minus f of A is equal to f dash of C into B minus A. The proof is actually quite simple. The idea is we construct an auxiliary function phi and apply Rolle's theorem to this auxiliary function. So what is this auxiliary function? So we define phi of x is equal to f of x minus f of A minus f of B minus f of A by B minus A into x minus A. Now this function might look a bit weird in the first glance, but actually it is not that weird. So suppose our function looks something like this. Say here this is A and this is f of A and this is say B and this is f of B. Then this quantity here is actually the equation of the line that joins AF of A to BF of B. So what are we doing? We are subtracting the equation of the line joining AF of A to BF of B from f of x. And in effect what it's doing is it's making that line into x-axis. But that might or might not be easily visualizable for you, but at least we can easily check that phi satisfies condition for Rolle's theorem. So if you look at phi of A is equal to f of A minus f of A minus f of A minus f of A by B minus A into A minus A. So this quantity is equal to 0, this quantity is equal to 0 and this quantity is equal to 0. So this whole phi of A is equal to 0. Similarly, phi of B is equal to f of B minus f of A minus f of B minus f of A by B minus A into B minus A. Okay, so this B minus A gets cancelled and we get f of B minus f of A minus f of B minus f of A, which is equal to 0. So both phi of A and phi of B is 0. Moreover, phi is continuous in the closed interval AB because it's the difference of two continuous functions. It's also differentiable in the open interval AB because f is differentiable in the open interval AB, and the other part, which is a linear function, is also differentiable in the open interval AB. So we can apply the Rolle's theorem to get that there exists a point C such that phi dash of C is equal to 0. But what is phi dash of C? Let's try to see that. I have rewritten phi of x for convenience. So phi dash of x is equal to f dash of x minus derivative of a constant which is equal to 0 minus, so again f of b minus f of a by b minus a is a constant, so that comes out. So we get f of b minus f of a by b minus a into derivative of x minus a. But the derivative of x minus a is equal to 1. So we get this is equal to f dash of x minus f of b minus f of a by b minus a. And we know that there exists some point C such that phi dash of C is equal to 0. So for that point we get f dash of C minus f of b minus f of a by b minus a is equal to 0, which is same as f dash of C is equal to f of b minus f of a by b minus a. And this gives us the theorem. So let's now try to understand what these theorems means geometrically. So Rolle's theorem tells that there exists a point on the graph of the function where the tangent is parallel to x-axis. So f dash of the slope being equal to 0 means it's parallel to x-axis, and f dash of c is equal to 0 means the slope of the tangent line is equal to 0. On the other hand, mean value theorem says that there exists a point where the tangent is actually parallel to the line connecting a comma f of a to b comma f of b. So this is the geometric intuition behind mean value theorem. However, mean value theorem is much deeper than this geometric intuition. But to understand the deeper meanings of mean value theorem, we have to wait till we learn integration. So hopefully we will revisit mean value theorem at that stage.